Now here we're looking at linear regression, simple linear regression. So what we're trying to do now is model the relationship between two variables as a straight line. So that's what we mean by simple linear regression. There's two variables. There's an independent variable x, which doesn't depend on the other variable by definition, and that thing drives the value of y, all right, which is the dependent variable. And the relationship is a straight line. That's what linear means, okay? So the act of regression is fitting a straight line between two data sets, essentially. All right, so the hit list here for this module, we need to think about what least squared regression is. All right, so least squared is a particular technique for calculating the coefficients of your regression equation. It's important that we understand how to calculate the intercept and the slope here. Now, just as a brief kind of warm-up, very basic kind of geometry, if you like, the equation for a line, when we're modeling y as a linear function of x, the equation is that y is some sort of constant intercept, all right, so that's just a constant, plus a slope coefficient multiplied by x. So the idea is as x changes, as x goes up and down, there's a sensitivity or slope coefficient that y has to it. Y will go up and down as well. When x is 0, y just takes this intercept, which is where we cut the y-axis by definition. All right, so very elementary back to school type comments there, but that does set up the basis for our modeling when it comes to linear regression. We're estimating this intercept from a sample. Notice we're doing estimation. We're hypothesizing really that the true relationship is this straight line, and we're using sampling to estimate what we think these coefficients are. Okay, we need to make assumptions along the way, and you need to know what those assumptions are. Some of them get quite left field names, if you like heteroskedasticity. We need to think about what those conditions are that we're imposing upon our modeling. And then we're going to wrap up with an analysis of variance, something called ANOVA. Analysis of variance really is thinking, it's an analysis of how good a job your model's doing, how good a job your x variable is doing at explaining variation in y. That's what analysis of variance is, and there's a couple of statistical tests there for us to do. Okay, so the starting point of any regression is really a visual one, and that is a scatter plot, as it's called, of the y variable, which in this case is the return on an individual stock, versus the x variable, which is the return on the market here. So each one of these dots is a paired observation. For example, this dot here, we see the market is up about 1.1, just over 1%, and the stock is up 2.5%, something like that. Okay, that's a paired observation. You've got lots of paired observations, might be days or weeks or months, and the job of regression, linear regression, is to model the relationship between y and x as a straight line. So here's our model. We're saying we believe that there's a true relationship between y and x as follows. There's an intercept, b0. There is a slope coefficient, b1. And there's always a little bit of noise in the model, right? So there's a random error term, okay, epsilon. And it's just random though. So in other words, we acknowledge in our model that the line doesn't do a perfect job at explaining how y varies with x. And it doesn't, does it? Because you can see those dots don't sit all on a line. Now, our job with the model is to estimate the best line. Okay, so you could put a line like that. Is that very good? Is that any good? Doesn't look perfect, does it? Or if we put a line like that, that doesn't look very good either. Remember, what we're doing here is really estimating B0 and B1 to come up with the line of best fit. The method chosen to do this under least squared regression is to pick B0 and B1, our estimates for them, such that the line gives us the lowest sum of squared residuals. So what does that mean? We're minimizing the sum of squared residuals. So what's a residual? A residual is the difference between our model, which is the line, okay? It's the difference between our model, the line, and what's actually observed. Now the model gets a letter y hat. That's your model. So a residual is the difference between your model and what's actually observed. Okay. In this case, for this particular data point, we're actually observing this dot here. The difference between that dot and the line is a residual, and technically that's a negative residual, isn't it? All right, because your actual observation yi is below your line, your model, which gets the letter y hat. Okay. Now, if you've got a well-specified model, those residuals should be random and they should cancel out because they're representing the random noise in your modeling relationship. So if you add them up, you should get 0. So we're not going to add them up when we're thinking about minimizing them, because they always add up to 0 anyway for a well-specified model. That's why we're going to add up the squares of them. So take these distances and square them so they all become positive, all these residuals, and then pick your B0 and your B1 such that you minimize the sum of the squared residuals. That's why it's called least squared regression. We're minimizing, pick a B0 and a B1 such that we minimize the sum of the squared residuals, okay? Such that your model, such that the model minimizes the sum of squared residuals. Now, just a technical point here. Your estimates for the true B0 and the true B1 are just that, they're estimates. So we're picking technically a B hat 0 and a B hat 1, and that's why we call our model y hat. Your model is technically y hat is B hat 0, that's your estimate for the intercept, okay, plus B hat 1, that's your estimate for the slope, all right, the true slope B1, all right, times x, okay, and then you've got you've got your residuals, and you're using your residuals to actually calibrate your B hat 0 and your B hat 1, okay. It turns out here for this particular data, the intercept B hat 0 is 0.5%, so that's your first term in your model here, and your slope, which is just the gradient of this line, is 0.9. So that's what you're going to use for forecasting. We forecast the residual to be 0 because a well-specified error term on average would be 0. Okay, so this is what you use for your forecasting when you put an x term in. This is what your best guess for what y would be. All right. So this is the idea behind the model, and this is you specifying over here. That's the idea behind the model, and this is you specifying the model. All right, specifying B0 and B1. Technically, this B0 hat and B1 hat here. Right, so what's important from your perspective is to just understand that we're minimizing the sum of the squares of these residuals, and that when you do that, there's a very specific way of calculating B hat 0, which is your best guess at B0, and B hat 1, or B1 hat, which is your best guess at the slope. And they are on the slide here. This is your specification for the model because it's got hats on. These are your estimates. The first one that I'm going to deal with is the slope. Your estimate for the slope is the covariance of x and y divided through by the variance of x. Now you might recognize that because we've already said that that is a slope coefficient in a regression. We've already said that that is a beta coefficient. In other areas of the curriculum we will say that. But this is a crucial definition that you need to learn. Okay, your estimate for a slope between two variables is how much y covaries with x relative to how much x covaries with itself, which of course is the variance of x. Okay, that is a killer app. All right, so that one needs to come in to your drop into your mental pocket. You're going to be using that on exam day. Just to give you a bit of cross-pollination there, that would be your estimate for beta under the capital asset pricing model. All right, so you get 2 for 1 if you learn that relationship. So make sure you're on that. Now, on the assumption that your model passes through means, in other words, it passes through x bar and y bar, and that is one of the assumptions of the model, that your line passes through both of the means together. at the same time. In other words, x bar, y bar lies on the line. If you put x bar into this equation and y bar into this equation and solve for given b hat 1, that's why we looked at it first, solve for what b hat 0 must be. Of course, b hat 0 is simply y bar minus b hat 1 lots of x bar. Okay, so that comes out of the statement that we pass through the mean x bar, y bar. If we talk at all about variation, we're really talking about sum of squared distances from means. Okay, just in the analysis that follows, if I ever talk about variation in x, I'm talking about the sum of squared distances away from the mean. All right, and if I talk about variation in y, I'm talking about sum of squared distances away from the mean of y bar. Okay. Right, now the assumptions of linear regression. What are they? Well, of course, it's a bit of a trivial one, isn't it? If you're modeling the relationship between x and y as a straight line, you are assuming the relationship between x and y is a straight line. It doesn't have to be a straight line, remember, but linear regression won't work for that. Okay. Other assumptions that we make for least square regression are less obvious. We do assume that the variance of the residuals is constant. The variance of those, essentially those error terms, they're constant. Now, that's the assumption of homoscedasticity. If we don't have homoscedasticity, then our data is not behaving in the same way across all of our regression range, if you like. And on that basis, it's changing. The nature of the relationship between x and y is changing, and we don't want the relationship to change. The fact that we're trying to capture a static equation over all this data that explains the relationship means the relationship must stay the same. Okay, so changes in the variance of the error term suggests that the sensitivity of x to changes in y is changing, all right, and we don't like that. That's the way to think about it. The pairs should be independent to each other, uncorrelated, and that comes through in the observation. How do we actually, if you like, check for that? How do we check that pairs aren't related to each other? So, for example, if we see a y that's above the line, an actual y that's above the line, how do we check that that's independent to other data points? We're not more likely to see a y above the line than usual if we've already seen one above the line, for example. Well, look at residuals. If the residuals are genuinely behaving randomly and aren't related to each other, then they're independent to each other and they're uncorrelated with each other, and we can say that actually there's no relationship between pairs of data. If you like, if you see a y above the line in a particular range, we don't expect, that doesn't give us any information about other observations in that area, or observations, say 4 periods before, if there's potentially seasonality and you're looking at quarters, for example. So key takeaway here is if the residuals are not correlated with lagged versions of themselves, or there's no pattern in your residuals with regards to correlation with each other, then you can be sure that your XY pairs are independent. But by the way, we do also assume, and this is very subtle, but we do also assume that residuals are normally distributed. So if you imagine it, the line like this, they're random, they're expected to be 0, and they're normally distributed around the line. There's no skewness, there's no kurtosis around the line, constant variance as well, so we don't get changes in that bell curve, the width of that corridor. That would be a well-formed regression. Now remember, those residuals, it doesn't feel like they contain much information because they're supposed to be just noise, but actually what we're saying here is if there's any pattern in them, any information in them, then that shouldn't be there, and so the regression is not well formed. That's the way to think about it. They're very interesting, these residuals, when we think about whether our regression is well formed. In other words, whether there's any issues with breaches of assumptions that we've made along the way. Okay, to look or test for breaches of these assumptions, at level 1, you're not going to do much other than just think about what the data would look like if it exhibited a breach of one of these assumptions, which you've kind of already done. But at level 2, we might come up with some formal statistical testing for breaches of these assumptions. A breach of linearity, for example, at level 1, it's good enough to just look at data and say, well, look, if we have a non-linear relationship between y and x, non-linear relationship. So clearly y is not following a straight line here as x varies around. You can see the straight line, the attempt to fit a straight line to it. It's not doing a great job. But there is some relationship between y and x, isn't there? It looks to be sort of quadratic or squared. So there will be some non-linear way of modelling this relationship, but a line's not doing a good job. So how might you see this? Well, you see it visually when you try and plot a line through it. Have a look at the residuals, and you start seeing that the residuals really depend on where x is. So you get negative residuals when we're in the middle there, and the curve is low. We get positive residuals at the end. So that might be a way of looking for non-linearity. Your line's not doing a very good job, and you see that the residuals are exhibiting some sort of pattern. It's a non-linear pattern. Okay, so that would be a breach of linearity, the first assumption. The second assumption, homoscedasticity, the breach of it would be heteroscedasticity. This would be where your, so number 2, breach of homoscedasticity is heteroscedasticity. This would be where the variance of your error terms changes and is not constant. So if you look at this data here, these dots, we've fitted a line to it. It should be fairly obvious from this data that if I kind of drew a corridor representing the volatility, or the variance, if you like, of the error term, it does expand here, doesn't it? It seems to expand when x is high. That's actually a breach of the assumption of homoscedasticity. The breach itself is referred to as heteroscedasticity. Okay, so the breach of homoscedasticity is this heteroscedasticity. You know, the implications of this we can discuss more at level 2, but right now, if you see a residuals plot where we see a lot more variance in errors when x is in a certain range and a lot lower variance elsewhere, you can either see it here, or you know, quite obviously you can see it there as well when we plot residuals. Then you've got a breach of heteroscedasticity. You've got a breach of homoscedasticity, which is called heteroscedasticity. All right, independence. We want our error terms to be independent of each other, remember. A classic breach of this would be that we see seasonality in our data. Look at this. We see that every fourth quarter, for example, we see a big sales figure come in, which is way above the line. All right, so that is a breach of independence of our error terms. You can say, well, if we're looking at December, we're going to get a big error, positive error. And why is that? Big positive residual, I should say, technically. And why is that? Well, because actually there's a relationship between errors in December and errors in the previous December. So that breaches the assumption of independence of errors. Very common for retailers, many sorts of businesses, that we do get higher sales in December, of course, the holiday season. All right. So, by the way, this breach of independence is referred to as autocorrelation. This is where a data set is correlated, or there is correlation with a lagged or past version, a lagged version of itself. All right, so when you're exhibiting autocorrelation, you're actually correlated with a value that you took in the past on a regular basis. And our example there is fourth quarter sales are always higher, so the error term exhibits autocorrelation with its value 4 quarters ago. Okay. When it comes to, so you can see this coming through here, by the way. You can see these massive residuals coming through here when we plot them explicitly. You know, residuals can be, this is kind of in brackets, residuals can be tested to see whether they're exhibiting normality. All right, you could interrogate visually a plot and see that there's more outliers, you know, more bigger residuals, say on one side of the line than the other. That would suggest skewness. It's hard to see kurtosis. You'd have to start thinking about formal tests for kurtosis. All right, but you know, in terms of thinking about the issue of a breach of assumptions, you're worried about higher order moments like skewness and excess kurtosis, which the normal distribution has none of, being exhibited in the data. Now, just a technical point here, for large sample sizes, they don't give a definition of large here, we can relax the normality assumption. So that's linked to, do you remember when we spoke about statistical testing, central limit theorem, we said if we've got large data sets, in that case it was 30 or above, then we didn't need the underlying distribution to be normal in order to apply the central limit theorem. Well, that's what's happening here. If we've got plenty of data, then we can apply the theory without a normally distributed underlying residual, okay? We don't need it to be normal if we've got a lot of data. That does tie in. Do you remember the central limit theorem walked away from hypothesis testing and said, I'm out, when we had small data size and we didn't know the population variance? Do you remember that? It's a similar comment to that. But just be aware the normality assumption can be relaxed if we've got a big data set. All right, now a crucial part of this reading, this module, is the analysis of variance. So by this stage, we should be comfortable that we're deriving our b hat 0 as an estimate for the true b0, just like x bar, the sample mean, is an estimate for the true blue mean mu, right? And we're estimating b hat 1, that's our estimate for the true b1. You know, if you've watched all these module videos, you know, whenever I look at a sample, I treat it as, I coloured it red to be clear it's coming from a sample. And whenever I was talking about population parameter, I made it blue. B hat naught is a guess at the true B naught. It's a guess and it's subject to noise, okay? It's important that you realise that just like X bar is a guess for the blue true mu, here we've got B hat naught and B hat 1, they're guesses, sample estimates if you like, for the true blue B naught and the true blue B1, the true blue slope B1, okay? So they're estimates, that's why I make them red, as I've done throughout all these videos, which means they're noisy. They will have a standard error, they will move around depending on which sample we look at. They will move around as we change our data. However, let's say we've got this data here and we've plotted a curve with that intercept and this slope, and that's our best guess through minimizing the square of residuals. Now, if I put those sample means on this chart, so when I say those, y bar, let's put it on here, that's the middle of the y data, sort of in the middle of all this y data, all right, and x bar in the middle of all the x values. Okay, let's put them on the map, and they'll sit in the middle, and you know the line passes through them as well, by the way. The line does pass through them. There's x bar, y bar, and the line is passing through it. Okay, so when we talk about analysis of variance, what happens is we pick an actual data point, like for example, that one there, and we say, okay, how much of the deviation in y from its mean, y bar, which is here, is explained by the model, and how much of it is residual? Okay, so that distance there at the top, that is your error that your model has got, or your residual, okay? So once again, we square so that negatives don't cancel out positives, but we can take the sum of squared errors, SSE, all right, sum of squared errors. Be careful with acronyms here. You've got to read them carefully because they look very similar, but if you get the wrong one, you're in trouble. So you can calculate the sum of squared errors. All you're really doing is calculating how far each actual observation is away from what your line says, your model, y hat, and squaring it and then adding them up, all right? We might even refer to this as the sum of your residuals squared, okay? Now that's unexplained. I want you to think of that as the model's not explaining that variation. What the model is explaining is this variation, because the model says, oh yeah, y should be about here. Okay, well, we've explained this distance in terms of deviation from the mean of y, and if what we can calculate here, we can square that so that negatives don't outweigh positives. We can square that and we can come up with the sum of squares of the regression. That's what SSR stands for, sum of squares of the regression. The important thing here is that you realize that this is explained variation in y. Okay, now for that particular data point, the model's not so hot. It's only explaining just about as much squared deviation, this bit here, you can tell by the distance, as is unexplained, not so hot. But generally across the model, we're adding these up, squaring them, and then adding them up. If you add together the SSE and the SSR, you get the SST, the sum of squares in total, or the sum of squares total. Okay, and yes, you just add them up. And actually, technically, SST is that whole distance, this whole distance here, all right, because the sum of squares do add up, all right. So that's your SST across your whole, across all of your data. Interestingly, look at that SST. The SST is actually the numerator of the sample variance, isn't it? Yeah, the SST is an old friend of ours. It's just the total variation in y in squared deviation terms. That's actually the numerator of the sample variance. So it's an old friend. Hello, old friend. Okay. All we're really doing here is breaking our old friend out into variation that's explained, which is a good thing, and variation which is not explained. There's always going to be some unexplained variation, but you know, when it starts to get very big, it means our line's not doing a very good job at explaining the relationship between the two data sets. Okay, so this forms the basis. This SSE, SSR forms the basis of our analysis of variance, and this ANOVA, as it's called for short, is actually often presented in a table, an ANOVA table. Here's an example of an ANOVA table for a regression with 5 data points. Now, it's not a lot, but we'll go with it. All right. The idea is we're breaking our variation out, our sums of squares out into sums of squares, a squared variation. We're breaking it out into that which is explained by the regression and that which is unexplained, and therefore is coming out in the residual. And yes, so this here in this table, to interpret what's going on, that would be your SSR, and that would be your SSE. Okay. Now, these sum of squares, I've already introduced. You know, when you combine these two, you can just by habit start adding these up. You'll get 95 spot 2 there. That's the SST. So just as a knee-jerk reaction, I'll add those up and get my SST just in case I need it. Remember, I described the SST as the numerator for variance. Now, you can think of SSR as like the numerator for explained variance and SSE as the numerator for unexplained variance. You can think of them like that. They're sums of squares associated with a variation that's explained by the model in the first row and variation that's not explained by the model in the second row. The question is, what do we divide those numerators by? Well, if you think about total variance, we divided total sample variance, we divided through by n-1 degrees of freedom. Okay, that was how free our data was when we fixed the sample mean and we didn't allow one of our data points to be free. Now, that's a comment that we made many modules ago. Crucial point is if you're calculating an average squared deviation, which is really like a variance, what you would do is take your total sum of squares, or SST, which is this, and divide through by your total degrees of freedom, which, by the way, is your sample size minus 1. We said that when we were calculating sample variance many modules ago. So the question here is, how many degrees of freedom are there for the regression, and how many degrees of freedom are there for the residual? Well, the way to think about this is to think how many sources there are, how many dimensions there are which can create this explained variation. And now the model that you're looking at here is y is b0 plus b1x and then some noise. This is unexplained, all right? It's the only dimension that, the only source that this explained variation can come from is from this one single independent factor, right? So there's one dimension from which these sum of squares are coming. This is the only explanatory variable, the only independent variable which is we're using to try and explain what y is doing. So our number of dimensions that we've got that are generating this explained sum of squares is 1. Okay, and more generally, if you're later on level 2, if you're doing multi-factor regression or multi-linear regression, there might be more than one independent x term, in which case more generally the degrees of freedom is actually the number of independent terms that you're using to model y. That's the number of dimensions or the number of sources you've got that can explain this, from which this explained sum of squares is coming. But for level 1 CFA, you can just think the degrees of freedom for the regression is 1 because it relates to my single x term, which is the single explanatory factor, essentially. That means that the degrees of freedom, which by the way still tot up. Do you remember my data here has got has got sample size of 5. My total degrees of freedom therefore is n minus 1, which there's a 4 popped up there, which is useful because that's what it is. All right. But my total degrees of freedom were n minus 1. Do you remember that? All right. So in this case, it's 5 minus 1. That's the denominator of the overall variance of y. Okay, you can just think the easy way to get to the degrees of freedom of the residual is that 1 plus something equals 4. This does tot up this column, and therefore the residual must be 3. Okay. More technically, this degrees of freedom of the residual, how free your errors really are, is your sample size, because any sample observation could take any value, but we're going to take off the number of independent terms in our model, number of independent x factors in our model. So that's often called k if you see that written in a text. So we're going to take them off because we fixed their mean to generate our model. We fixed 1 x bar, and that removed a degree of freedom. We'll do that for every factor that we've used, every independent factor that we've used. We also take off 1 as well because we fixed y bar. So technically the number of degrees of freedom of the residual is n minus the number of independent factors minus 1. All right, but in this case, if you use that, you can go 5 minus 1 x factor minus 1, which is 3. And the easier way to do it, as I've said, is to simply say your total degrees of freedom is n minus 1, which is the denominator of the overall variance of y, as it always is on for a sample variance. And then your degrees of freedom of the regression is number of x factors, x variables, which is 1. And so clearly the degrees of freedom of the residual must be 4 minus 1, which is 3. Okay, so there you go. That's the degrees of freedom, and the slide has been, the slide is giving us those in more general terms. Okay, we can calculate the total sum squares. I spoiled that one. Many apologies to those wanting to see the animation come up in order. I can't help but calculate the total sum squares. You saw me do it as 95.2. It's like a knee-jerk reaction to seeing that column. We just tot it up. And now, this column here, so if that's column number 1, the degrees of freedom, column number 2 is the sum of squares, column number 3 is like a variance column. In fact, if you took, for row 3, the total row, if you took the total sum of squares, or the sum of squares in total, and you divide it by the total degrees of freedom, you do get variance of the data, the variance of y. All right. However, that's not massively of interest to us. What's more interesting is what happens when you do that for the other rows. If you take essentially what's in column 2, all right, if you think about this mean square, if you take what's in column 2 and you divide it by what's in column 1, in other words, if you take the sum of squares and divide by the degrees of freedom, you'll get what's called a mean square, an average square deviation, which is like a variance term in inverted commas. So the variance associated with your regression, which is explained, is 88 divided by 1. That's column 2 divided by column 1. And the mean square of the residual, which is the variance which is unexplained in your model, is 7.2 divided by 3, which is 2.4. Okay? Now they're very important terms. Very important terms. The general idea is that column 3 is column 2 divided by column 1. And by the way, if you do that for the third row, which we don't do explicitly, you would get the variance of the data. And you can see there the essence of what we're doing. Mean square is really a variance term in inverted commas. It's like your average squared deviation coming from the number of sources that they could come from. Now, in order to do what's called a global test on your regression, what we might assume for a global test of the regression, so let's write this out. If we do a global test of the regression, we're testing the whole regression at once. That's what we mean by global test of the regression. Our null hypothesis is going to be that none of our coefficients that we're using, and there might only be one, but there might be more than one when we're doing multi-linear regression later on. You do a lot of that at level 2. Our null hypothesis is that all of our coefficients that we're using, all right, all of the coefficients that we're using in our model are 0. So none of our factors have explanatory power. That's a dull null. Like, why did we bother going in and setting up our model? It's all a waste of time. Dull null. All right. The alternative is that, now what's the alternative of all of our coefficients are 0? It's not that all of our coefficients are non-zero. That's bad logic and bad grammar as well, right? You know, the opposite of it, of H0, is that at least one of our coefficients is non-zero. And we're talking here about slope coefficients. You might very well wonder why are we saying at least one? Well, because we can apply this to multilinear regression, where we haven't just got b hat 0 and b hat 1 as estimates for intercept and one slope coefficient. We might have b hat 2 as well as an estimate for a second slope coefficient against a second independent variable, and b hat 3 and so on, right? We haven't got those at level 1 CFA because it's simple linear regression, which means there's only one x independent variable, all right? But so you can read this at level 1. You can say, you know, the global test of regression, when we use an F statistic, we're going to use an F statistic here, which we're coming on to. You remember that F stat, by the way, was used in a previous module to, do you remember we used that, the F distribution, when we were comparing variances? Yeah, we're going to do it again. We're really comparing variances here. As far as you're concerned for level 1, you can view these hypotheses as H0 is that our B1 coefficient is actually 0, right? And the alternative is that actually it's non-zero, which is exciting. Okay, so going back to the ANOVA table that we're looking at, let's give these two items a name. So that 88 there, think of it as the variance that it's explained by our model. That's called the mean square of the regression. And this variance here that's unexplained because it's linked to the residual, that's the mean square error. More 3-letter acronyms, so be careful. All right. We're going to use an F stat, which is really just comparing our explained variance, MSR, to our unexplained variance, MSE, to conduct this global test of the regression. The F stat itself is very, very straightforward. The test statistic that you're getting out of your table here, it just looks at the explained variance, the MSR, relative to the unexplained variance, the MSE. We've got them in our table, so we can calculate that. 88 divided by 2.4, 36.67. That is a test statistic. It follows an F distribution with degrees of freedom on the numerator of 1 and degrees of freedom on the denominator of 3. You've already got those degrees of freedom sitting there in the table. Now, you go to an F table like we've done before. If you're doing a 5% significant test, go to the 95th percentile. In other words, pick out for those degrees of freedom the value for F such that there's only 5% in the right-hand tail and 95% under the bell. And we see that when we pick out that critical value, we get 10.1 for the F statistic. Okay, now you can go to F tables and look at that, or it'll be given to you in a question, and an extract from the F table will be given to you in the question. So you can strip out that 10.1. What have we seen? We've seen something that's very, very big relative to that 10.1. So we reject the null hypothesis that all coefficients are 0. That was a null hypothesis we made off slide here, and we didn't like that. Rejecting it is to be celebrated. It means that at least one of our slope coefficients is extremely unlikely to be 0, all right, and it's non-zero therefore. And given that we're in a single factor environment, in other words, there's only one x variable, that means the factor that we've chosen has got some explanatory power when it comes to explaining what y is actually doing. So that's great. Now, another thing you need to strip out of the ANOVA table is an R-squared coefficient. So what's an R-squared coefficient? Its official name, its formal name is the coefficient of determination, and it's the level of variation in y, proportion of variation in y that is explained by the model. So you would look at the sum of squares, you would take the explained sum of squares, and you'd think, how big is that out of my total sum of squares? All right, that's a very common sense and straightforward measure. The answer here is 88 divided by 95 spot 2, which is an enormous 92 spot 4%. You can think that 92 spot 4% of the variation in y is explained, which is probably a bit too good, actually. It's a bit too good to be true. We did see a massive f-stat compared to the critical value, which, you know, these things are going to be related, right? Big f-stat means lots of explanatory power, and so large r squared. In terms of another statistic that you could strip out of this table, unfortunately we get a rather nasty acronym to finish off here. We get a name, so just be careful with this one. This one's a bit of a poison one. The standard error of the estimate. If you ever see that, the standard error of the estimate, SEE or S little e, that, in my mind, I just think very carefully. I don't call it that because that's not the useful name. That's kind of like putting a disguise on it. I call it the volatility of the residual. Okay, volatility of the residual. So we're looking here at our standard deviation S of the residual term, SE. That's good. It's also called standard error of the estimate. Okay. Of course, if this here is a proxy for variance of the error term, then take the square root of that, MSE, and you'll get back to an estimate of the volatility or the standard deviation of the residual. Okay, so be very careful with that, because SEE, the standard error of the estimate, which is really just the volatility of the residual, that looks a lot like SSE. But it's not the same thing, is it? That's the volatility of the residual, and that is the sum of squared errors. In other words, the sum of your errors after you've squared them. You square them and then sum them. Now, don't forget, by the way, that whilst they're not the same thing, they are related. Your standard error of the estimate, I'm just going to write up what it stands for so that we've got perfect visibility here. Standard error of the estimate is the volatility of your error term, okay, your residual. And the volatility of your residual, of course, is the square root of the variance of your residual. Your unexplained variance is referred to as the MSE, okay? And your MSE, if you think about it, it's how far I am away from an expected value of 0 squared, summed up. So my squared deviations. If you like, sum up my error terms across all of them, minus 0 squared, right, divided by the degrees of freedom associated with the error term, which we've already said is n minus the number of x factors. All right, k here is the number of independent terms, independent factors, number of x variables you're using, minus 1. We've already said that that is the degrees of freedom of the residual. We've already said that's the degrees of freedom of the residual in the ANOVA table. So that's nothing new there. It looks ugly, but there's nothing new. By the way, I can write this, drop the 0, write it as the square root of the sum of the squared errors divided by the degrees of freedom of the residual, which when k is 1, there's only one x term, you get n minus 2. All right, and look at that. That is SSE. So be super careful here. That's actually SSE over n minus 2. Just be super careful. When you're reading through text and stuff, if you read it too quickly, SEE, SSE, they look like the same thing. They're not the same thing, and they are actually related to each other in this way. So be super careful with this. So now we're going to look at testing an individual coefficient. Rather than testing the regression as a whole with an f-test, we're going to test an individual coefficient to see whether it's significantly different from 0. You might sort of wonder why we're doing this, because it feels like with one independent factor x, a global test is a test of the one independent factor, and a t-test of the individual coefficient would be a test of the one individual factor. So it looks like we're duplicating work here. The response to that is a response that I've given a couple of times, and that is when you get into multivariate linear regression, when y is related to, or you're modeling that y is related to many different x variables like x1, x2, and so on, and an error term, then actually it might be worthwhile, once you've, with a global test of the regression, once you've decided that at least one of these coefficients is non-zero, b1, b2, up to what they call bk, then you might interrogate each one individually to see which one it is. Okay, so that's what we're doing here. In our simple linear regression world, we're really just looking at our estimate for b hat 1, and we're thinking, is there evidence that this is statistically different from 0? So here's your estimated slope, 150. Now that's an estimated slope, so we are estimating b1. That actually technically though is b hat 1. That's our estimate for it. Okay, so that should have a hat on here. And now this is very important. This is the standard error of the slope coefficient. All right, standard error of b hat 1. Now some of you will sort of be thinking, I thought standard error was, you know, something we spoke about with x bar, the sample mean. And the answer is, yeah, we did. But the idea of a standard error is a general one. Now, the standard error is the dispersion of an estimator. It's the volatility of an estimator. All right. So the way to think about this is, if you took lots of regressions, you'd find your slope that you get each time would bounce around. It would vary. And that's what this standard error is telling you. It's the dispersion of the different slopes you're likely to get given the features of the population and given the features of the sample slope coefficient that you're calculating. Okay, so just think of it as a dispersion, like a standard deviation, just like we thought of the standard error for x bar. Given a data size of 32, we are going to test the assertion that the true blue B1, all right, so we've got to make the distinction between the true blue B1 and your estimated B1. If you hypothesize that it's really 0, hopefully we can reject that, given that we've seen a sample B hat 1 from our regression that's a long way away from what we've hypothesized, a value of 0, right? In terms of standard errors. There's the standard error popping up there. All right, this is no different to calculating a test stat for a single mean, where we said we're interested in how many standard deviations our sample mean is from a hypothesized true blue mu in terms of the standard error of x bar. It's exactly the same as that. Do you remember that? We did that a lot in previous modules. It's exactly the same as that. Take your regression sample estimate, all right, see how far away that is from a hypothesized value in terms of standard errors. We get 1.5, like I say, technically that's b hat b1 hat minus a hypothesized value of 0 divided by that standard error of b hat 1 0.46. So we're 3.26 standard errors away from a hypothesized value of 0 at 5% significance when you're doing a t-test, which this is. It's a single estimator, so generally these are t-tests. You can think 2 will do, right? 2 will do, capturing 95% of the distribution. So actually we're not within that range, so the original hypothesized mu is unlikely to be correct. If you go to a t-table, you'll get, apologies for the mess there, if you go to a t-table, you'll get an exact t-value with 30 degrees of freedom. So here, to be exact, our degrees of freedom for our overall regression would be n minus the number of x variables we're using, k minus 1. With simple linear regression, we're always using one x variable. So the degrees of freedom would be n minus 2, which is 32 minus 2, which is 30. So if you go to the table, you're wasting time here, but if you do go to the table and you look up 30 degrees of freedom, 5% significance with 2 tails, in other words 2.5% in each individual tail, you'll get about 2. And like I said, 2 will do at the start, right? You've got to start becoming a little bit of a practical person when it comes to statistical testing and thinking, well, 3's much bigger than the 2 that's associated with 95% confidence interval or 5% 2 tail, 5% significance 2 tail. So what do we do with this idea that B1 is actually 0? The true B1 is actually 0. We reject it because we've seen something that is too far away from our hypothesized value of 0. It's 3.26 standard errors away, when actually we're not willing to observe something that's more than 2.042 standard errors away, because that's what we'd see 95% under that null assumption. So that's another example of a hypothesis test there. Okay, now once you've specified a model, it's quite simple to take your estimated values for B0 and B1. Technically that's B hat 0 and B hat 1 coming out of your regression, and put a value of X in, all right, and come out with a point estimate for what you think Y is going to be, a predicted value. So that would be just using your model. This is quite trivial. You know, if you think that if you think you're going to see, or you do have a reading of 8% for the independent term, then if you plug that into your model, you'll just get B hat 0 of 1.8 plus the slope coefficient 0.76 times your X value, and plug that through, you'll get 7.88. That's your line. So if you're modeling where you're going to be, that's your line where X is 8. You're modeling that you'll be at 7.88%. Now, the truth is, you know as a statistician that your line is only an estimate, and actually there's a couple of reasons why your line estimate here, your point estimate of your line is going to be wrong. The first reason, of course, is you've got residuals, and there's the volatility of the residual, right? So we often see, we see a cloud of data around the line, we don't see the line itself. So there's the error term, if you like, the sources of randomness that would affect the accuracy of our prediction would be the residual, the error term, okay? Plus, don't forget, our estimates are random. There's sample estimates as well, so they're actually random variables themselves. There's going to be some sampling error to do with B hat 0 and B hat 1. There's going to be some sampling error. Remember, that's where our guess based on a sample is different to the true blue population parameter, in this case the true B0 and the true B1. So there's going to be sampling error in B hat 0 and B hat 1. Now, the further you go away from the mean of your data, the bigger that sampling error becomes. We can capture this noise, all right, and come up with what are called prediction intervals around our line. It turns out that the prediction intervals are actually narrower when we're in the middle of the data. They're actually wider when we go away from the middle of the data, when we go away from our X bar. That'll be X bar in the middle there. They're actually wider because there's more uncertainty as you move away from the middle of the data. But these confidence intervals, they get a special name. They're called prediction intervals. They're intervals where you're, say, 95% sure you will observe your Y value, given a value for X, say, all right? And they capture all sources of randomness, all sources of potential error. That is the residual itself, the volatility of the residual itself, and sampling error with your B hat 0 and your B hat 1, okay? To capture all of these sources of randomness, you might very well be given the standard error of the forecast. All right, now this is the last technical term that you need to get your head around. Standard error of the forecast, often labeled as SF, all right? If you've got the standard error of the forecast, then what you've got really is the distance, that you need to go, if you like, your unit of distance that you need to go either side of your line to capture 95%, a 95% chance that the true Y will be in that range, okay? So for our forecast here of 7.88, that kind of dot estimate on the line, what we know is if we're given a standard error of the forecast, you've got to read really carefully here because there's lots of uses of standard error. If we're given the standard error of the forecast, the crucial word is forecast, what we can do is bolt a multiple, just like our Z and T values, all right? A multiple of that standard error of the forecast around, vertically think, around that guess to get these what are called prediction intervals. So let's do that. If you're given, we know that we're predicting a point estimate of 7.8, we just did that, 7.88. If we get given the standard error of the forecast, and the crucial word there is forecast, that's the whole regression we're using to make forecasts of 1.22, what we can say is, and there's our N of 27 observations, what we can say is we can create a 95% prediction interval by placing a critical value with 25 degrees of freedom. That would be our N minus, once again, 1x term minus 1 for the y term, so that's n minus 2, as you can see. 2 will do, by the way, for 95% with 2 tails. All right, but we'll go with 2.06 here. We get given that. What we're going to do is we're going to take that multiple and bolt that critical t distance number of standard errors of the forecast around our estimated 7.88. Okay, so this range here, 537 to 1039, that is the range that we are 95% confident, right? So our guess was 7.88, and our range that we are 95% confident we'll observe y in is 537 to 1039. So it starts at 537 and it ends at 1039. Okay, that's what we've just calculated there. It's an application of a confidence interval, but it's technically called a prediction interval because you're using the model to predict where you're 95% confident you think y is going to be for a given value of x. Now, the formula for the standard error of the forecast is in the text, but I think it's one of those formulae that does more harm than good. You know, they just throw it at you, they don't statistically justify it, and it puts a lot of people off. And the people that could get this mark for knowing what it is, knowing the difference between the standard error of the forecast and the standard error of the estimate, all right, you know, that sort of thing, those people are going to be picking up the very common marks in the exam, and that you don't need to calculate the standard error of the forecast. Having said that, for what it's worth, the standard error of the forecast is derived as follows. The standard error of the forecast squared, so that's like in variance terms, is your standard error of the estimate squared. So that is really the variance of the error term that you've got in your model, SEE. All right, squared. So that's the variance of the error term. And then you adjust it for 1 plus 1 over n. So 1 over n here, that will dissipate to 0. That's really punishing you if you haven't got a lot of data. 1 over n will be quite big if you haven't got a lot of data. If you have got a lot of data, that will dissipate to 0. And then this term here is really reflecting how far you are or where you are in your data. Remember I said that the further you are away from the center of your data, the wider these prediction intervals need to be because there's less certainty about how x and y are interacting out there. So that's what this term is representing. If you look at it, this is how far your x observation is away from the mean squared. And we're thinking how big that is relative to, what's this on the bottom? Well, n minus 1 times the sample variance is just the sum of squared deviations in your x term. All right? In other words, your variation. It's the numerator of the variance, isn't it? It's the variation in x. So we're really looking here at how far away the term is that you're using to get your prediction from the mean squared relative to the sum of all the squared deviations in x. It's the proportion of the variance of x that this term is comprising, essentially, or it's the proportion of the sum of squared deviations of x that this term is making up. Okay. Now, I don't think I put this to the back of the queue, this one. I wouldn't worry about learning this one straight off the bat. All of the other stuff that we've spoken about is more important than that formula. Don't let it put you off. Okay, put it to the back of the queue. And also be aware if n is large, then n goes to infinity. This becomes very big and the whole 1 over n dissipates. And this becomes very big and that dissipates. In other words, the standard error of the forecast, capturing all sources of variance, is actually similar to the standard error of the estimate, which is the variance of the error term, okay, for large samples. Okay, now the final point in this reading looks at different functional forms for linear regressions. The point here is that we don't always just model y versus x as a straight line. One of the things that is used quite a lot in modeling is that actually if we model logarithms, then what we're capturing is continuously compounded rates of change. You might remember that when we calculate continuously compounded returns, a continuously compounded return is actually the logarithm of 1 plus what we earn. So actually the change in a logarithm represents the logarithm of a variable, like a price, something like that. That actually represents your continuously compounded return. All right. It's something that you need to really get comfortable with, that the change in a logarithm is the same as the continuously compounded return, because continuously compounded returns are based on logarithms, right? I'm stating that quite informally. If there's any maths police out there, don't shoot me. We're just getting to the chase quickly. Changes in logarithms represent continuously compounded returns. So if you decide you're going to model the logarithm of y as being driven by x, then what you're really saying is that an absolute change in x drives a percentage change in continuously compounded terms in y. All right. You've got to be careful using this model, because what you're actually looking at here when you look at this model, of course, is say the logarithm of y is b hat 0 plus b hat 1 lots of x, and then an error term. If you put an x in, you don't get y, you get the logarithm of y. Remember that the logarithm is the opposite of the exponential function. In order to get back to y, you have to put the exponential constant to the logarithm of y. The e and the ln cancel out, and you're just left with y. All right. So I don't think you'll be doing that. It's more for level 2, but just be aware that this is referred to as a log-lin model, because x remains untouched, but we're taking logarithms of the y. You could have it the other way around. You could view that a percentage change in continuously compounded terms for x drives an absolute change in y, or you could even say that sometimes we'd be modeling percentage changes in x driving percentage changes in y, okay, and they'd both be logarithms. Crucial thing is that changes in logarithms are continuously compounded returns, and so that's where that absolute change becomes actually a relative change in terms of percent, okay. If you do any of these changes in functional forms, this is just a qualitative comment. You won't be doing this, not at level 1 anyway. If you do change any functional form, the important thing is to really check that the change in functional form is worth it. In other words, your model's doing a better job by having a higher R squared, a better F-stat, higher F-stat, and a lower standard error of the estimate. Don't forget, standard error of the estimate, of course, is the volatility of the error term. Okay, well, that wraps up this particular module. We saw a lot of stuff there. Focus on particularly the ANOVA tables, the 3-letter acronyms, things like MSR, SSE, MSE, SEE, all these things. You must know what they are. You must be able to differentiate between them, because they lend themselves to a very small, compact question, which dives quite deep into your knowledge base. Okay, so that completes this module.